Now it's time to look at how parallel computers may look. So they come in many different forms and shapes. I'm going to look at four different classes of parallel computer systems in general. So before I talked mostly about multi-core architectures, but and this is just one of them. So a typical multi-core architecture is a processor which has several cores on the same chip, and it's all about sort of the cache hierarchy on these chips. So this picture shows a system with 8 cores. Those are the red, the blue squares here. And the green boxes are cache memories. So typically, these these cores have private level 1 caches for instructions and data. And there is typically a shared last level cache. Most processors today it's the last level cache is equal to the level 3 cache. But then there might be one or more levels of intermediate caches that may or may not be in smaller subsets. They may be private for each core, or they may be by groups of cores and so on. Multi-core architectures are characterized by that they are shared memory, which means that the last level cache is shared, and of course the off-chip memory. So there is always one or more memory managers to interface to dynamic random access memory. But also these caches sort of can contain shared data. So there is a cache coherence protocol that makes all this work. The next kind of model I'm going to talk about are NUMA, or non-uniform memory architecture processors. In a NUMA architecture, we have processors that may or may not be multi-core processors. So each one of these boxes here can have 1 to typically 16 cores in them. There may be more if you like, but this is the most common variants. And then each chip here, or each processor module here, has interface to its part of the shared memory. This means, of course, that and then these processors are interconnected by some kind of interconnect mechanism, and with the dominant processor manufacturers, which is Intel and AMD in this case, they have different kinds of links. So in Intel you have QuickPath, in AMD processors you have HyperTransport, and there are various variants. And these links here make it possible for cores in this processor here to access both this data and data connected to some other processor. Of course, this processor here has faster access to its memory than if it has to go to other links. And this is where the non-uniformity comes into play. So this is a non-uniform memory architecture, in contrast to SMP, which stands for symmetric multiprocessing. But it's still shared memory, and the memory caches are coherent. The third kind of architecture is called heterogeneous architectures. In a heterogeneous architecture, we have a typically homogeneous system. It can be an SMP or it can be a NUMA processor connected to some I/O bus, which in most cases is a PCI bus. And then we can connect to this PCI bus heterogeneous or accelerators. For instance, it can be GPUs. It can be a many-core interconnected architecture like the Intel Xeon Phi. Those are the two most common ones, but it could also be an FPGA where you dynamically can generate new kind of designs and so on. This is a very hot topic in parallel computing nowadays, and the challenge here is, of course, how do you program these in the best possible way. And finally, we have large parallel systems. In high-performance computing areas, you have clusters. So you cluster all of these things together. So this is an example of a Cray XE30, where you have blade cards here that consists of maybe 8 CPU modules connected to a network, and each sort of connection to the network consists of 2 processors and some memory. So it's each one of these is a NUMA architecture. Each CPU is a multi-core, and then they are connected. And you only have shared memory basically within a NUMA node between the individual nodes here. And this is a very scalable system, so you can build this with tens or hundreds of thousands of processors. And between these nodes, there is no shared memory, and you have to resort to other kinds of communication like message passing and so on. This is beyond the scope of this course. We'll deal mostly what's happening within a node here.